All right, today we're looking at trig substitution. The idea behind trig substitution is instead of just substituting a u into a function, we're going to say, okay, a trig function would be better suited here, and we have some ways we can rearrange things, so we're going to substitute trig functions in to be able to make it so we can integrate it. They're going to use three triangles for trig substitution. First one is the sine triangle. It's used whenever we have a constant squared minus a function squared. And it is designed so that sine is equal to u over a, the function over the constant. Tangent triangle done the same way. It does a constant squared plus a function squared. Once again, tangent is equal to u over a. And then lastly is the secant squared. This is function minus constant squared, function squared minus constant squared. And once again, secant is equal to u over a. Now, the idea is we're looking for these patterns that say, oh, I can use trig substitution. It's not always going to be the best option. A perfect example is this one right here. Integral dx over 9 plus x squared. If you've been watching my videos or in class, you know that this is an inverse trig function. We can integrate, say this is 1/3 arctangent x over 3. We know that. It's a very easy inverse trig integral. But this also falls within a trig substitution. We have a constant squared plus a function squared. We have 3 squared plus x squared. So let's do this with trig substitution just to show that it's not always the best way to do it. Obviously, the inverse trig is the best option, but also to show that it does work, to verify that this does work for us. Because we have a constant plus a function, we're going to use our tangent triangle. So this is our theta. We have u over a, so x over 3, and then square root of 9 plus x squared. We're going to say tangent is 3 tangent theta is equal to x. And the first thing we're going to do is we're going to find dx, because we have dx on top there. Easiest way to get dx is to take the derivative of this. So it's 3 secant squared theta d theta. So we can substitute that in. 3 secant squared theta d theta. That's our dx. Now we need to find 9 plus x squared. So we're going to pick a trig function that uses 9 plus x squared and will let us isolate it. Now the key is, there's 6 trig functions we can pick from here. All of them will let us, well, most of them will let us get 9 plus x squared by itself. But we want to get 9 plus x squared by itself and not have any x's on the other side. So the best option is going to be either secant or cosine. Cosine uses adjacent over hypotenuse. That puts it on the denominator. We don't want that, so we'll use secant. Equals square root 9 plus x squared over 3. Multiply both sides by 3. Okay, and then we're going to undo that square. To undo the square, or the square root, we're going to square both sides. So we have 9 secant squared theta equals 9 plus x squared. Now we can substitute in for 9 plus x squared. 9 secant squared theta d theta. We'll simplify. We get 1 over 3. Integral of, well, secant squared over secant squared is just 1 d theta. The integral of 1 is theta plus c. And then we can find theta by going back to this right here and solving for theta. Divide by 3, do the inverse tangent of the other side. So 1/3 arctangent x over 3 plus c. And so this does work. It gives us the correct answer. It is a way to substitute in things that we can now integrate. It just is a much longer way than just knowing the integral of 1 over 9 plus x squared is equal to 1/3 arctangent x over 3. Let's look at another one that it becomes more useful on. So one like this. 4 plus x squared, if it was by itself on the denominator, would be great. That'd be fine. But when we throw that square root in there, it becomes a much bigger issue. We can't deal with that square root because our inverse trig function doesn't perfectly match. So this is where the triangle is going to come in. We're going to use the same exact triangle. X, 2 square root 4 plus x squared. We're going to say x equals tangent theta, 2 tangent theta. Dx equals 2 secant squared theta. So we know dx. We can find the square root of 4 plus x squared by using secant again. So 2 secant theta equals square root 4 plus x squared. All right, so we have the integral of, there should be a d theta here, of 2 secant squared theta d theta over 2 secant theta by itself. We'll simplify, we get integral secant theta d theta. And now we need to integrate secant theta. And this is a very weird integral. If you're in class, I would show you how we get this, but I'm just going to tell you right now in video how to do it. And if you have a question, please come ask me how we got it. So the integral of secant is just natural log absolute value secant theta plus tangent theta. Now a lot of people are going to get here and they're going to be like, "Whew, I'm done. This is a hard problem. I had a lot to do," but you're not done yet because we had x's in the original, and we have thetas in our problem right now. So we need to substitute these back in using our triangle. So secant is square root 4 plus x squared, 4 plus x squared over 2. Tangent is just x over 2. And for most cases, I'd be like, okay, we don't need to simplify much more, but this is one case where you definitely need to simplify. Since they're both divided by 2, we can separate the natural log, and the natural log absolute value is square root 4 plus x squared plus x minus natural log of 2 plus c. And the reason we do this is because this natural log of 2 is a constant, so it gets combined with the c there to just be plus c at the end. And that is a form of simplification you have to do. All right, so you need to know the integral of secant. The integral of cosecant is very similar. Integral of cosecant is just going to be negative natural log absolute value cosecant theta, or cosecant theta, theta plus cotangent theta plus c. Okay, if you need that one. All right, and that's really trig substitution. So you're going to be identifying what triangle to use and then trying to rearrange to substitute things in as needed. Let me know if you have any questions. Y'all have a great day.